The next important piece of AI hardware might not be a GPU. It might be the SSD already sitting inside your laptop. That sounds ridiculous. SSDs store files, GPUs run models. One is a filing cabinet, the other is a factory. Then a project called Colibri ran GLM 5.2, a 744 billion parameter open model on a consumer machine with roughly 25 gigabytes of RAM. The compressed model occupies about 370 gigabytes. It is around 15 times larger than the memory available to run it. No data center, no rack of GPUs. The machine does not even need a GPU to make the model answer. There is a catch, and it is a brutal one. On the original laptop, generation crawled at roughly 1 token every 10 seconds. A normal answer could take hours. So no, this is not a replacement for ChatGPT on your lunch break. It proves something more interesting. An AI model no longer has to fit inside memory before a computer can run it. That changes what local AI means. The model can live on the SSD. The computer loads only the pieces needed for the next token, throws away the cold pieces, and repeats. The SSD stops behaving like storage. It becomes the slowest layer of memory. A traditional language model needs nearly all its weights every time it generates a token. If the model occupies 370 gigabytes and your machine has 25 gigabytes of RAM, you have a simple problem. It does not fit. You could read the weights directly from the SSD, but then every token would require hundreds of gigabytes of disk traffic. Even a very fast consumer drive would take far too long. One word could become a coffee break. This is why large models normally live across expensive GPUs. Their memory is fast enough to keep the weights close to the processors performing the calculations. Colibri cannot make an SSD as fast as GPU memory. It avoids reading most of the model. GLM 5.2 is a mixture of experts model. Inside its expert layers are 256 separate blocks of learned weights. A small router examines each token and selects 8 of those blocks to process it. The others remain inactive. Out of 744 billion total parameters, roughly 40 billion participate in a token. That is still an enormous amount of computation, but it reveals the opening Colibri needs. Most of the model exists so it can be available when required. Most of it is not required right now. We tend to talk about model size as if every parameter works on every answer. In a sparse model, that number confuses total capacity with the active working set. A 744 billion parameter model does not perform 744 billion parameters of work for each token. That difference is large enough to drive an SSD through. The name mixture of experts creates a misleading picture. You might imagine one expert for mathematics, one for Python, one for legal writing, and another for poetry. If the model is being used for code, perhaps you could keep the coding expert and delete everything else. The network is not organized that cleanly. Experts are blocks of learned weights with overlapping, difficult-to-label behavior. The router may select different experts for the same word depending on the sentence, the token position, and the layer processing it. There is no neat folder called JavaScript. Colibri cannot shrink the model by keeping only the useful experts because usefulness changes constantly. Instead, it treats the experts like a huge library. A small, dense portion of the model is needed for every token. At 4-bit precision, that section occupies just under 10 gigabytes, so Colibri keeps it in RAM. The routed experts occupy roughly 370 gigabytes. Those remain on the SSD. When a token reaches a layer, the router selects the experts needed for that step. Colibri checks whether they are already cached in RAM. If an expert is present, the processor uses it immediately. If it is missing, Colibri reads that specific block from its exact location on the SSD. When the cache fills, an expert that has remained unused gets evicted. The process repeats across the model. A completely cold token can still require around 11 gigabytes of disk reads. That is an absurd amount of traffic for one token, but it is far less than reading the entire model. The trick is not making storage fast. It is becoming ruthless about what deserves to enter memory. Expert usage is not random. Certain experts receive much more traffic than others. A person repeatedly using the model for one type of work may create a recognizable pattern of hot and cold experts. Colibri records that activity. On a later launch, it can use the spare RAM for experts that appeared frequently in previous sessions. The dense core remains resident, while the cache gradually becomes more useful for that person's workload. The model does not become more intelligent as you use it. The engine becomes better at placing its weights. Colibri also knows which experts the router selected before the program requests them from storage. That gives it an advantage over ordinary memory mapping. An operating system can map a model file and load pages when software touches them, but a page fault is reactive. The program asks for missing data, the thread waits, and the operating system retrieves it. Colibri sees the router's decision first. It can request multiple experts asynchronously while the CPU continues working. It can also run the next routing decision early and begin fetching likely experts before that layer needs them. Its router look-ahead has reported predictive accuracy of roughly 72%. Prediction does not remove the SSD bottleneck, but it can move some weighting into the background. This is the part of the project that matters beyond one model. If expert routing is predictable enough, runtimes can treat model weights as a hierarchy. The hottest weights live in GPU memory. Warm weights live in system RAM. Cold weights remain on the SSD. The system moves them according to measured demand. That is how computers already manage caches and virtual memory. Colibri applies the same idea to the internal pieces of an AI model. Now for the number that ruins the demo. On the original consumer machine, Colibri reportedly generated around 0.05 to 0.1 tokens per second. At 0.1 tokens per second, a 500-token answer takes well over an hour. Faster SSDs, more RAM, and better hardware improve the result. Community tests have ranged from a fraction of a token per second to around 1 token per second on powerful consumer systems. That is still nowhere near the speed people expect from an interactive assistant. If you want a rapid coding conversation, use the largest model that fits in fast memory. Waiting 10 seconds for every token will make you hate both the model and your computer. But interactive chat is not every workload. At 0.1 tokens per second, the system can still generate about 8,000 tokens in a day. That could be several long answers produced overnight without sending the prompt to an external API. For an air-gapped machine, sensitive documents, legally restricted data, or an overnight code analysis, the clock may matter less than privacy and model quality. I find that trade strangely appealing. Cloud AI trains us to think intelligence must arrive instantly through an API. Colibri asks whether some intelligence can arrive slowly, privately, and entirely under your control. This creates the argument, does a model count as locally usable if one answer takes an hour? For chat, probably not. For a task that can run while you sleep, the answer becomes less obvious. Colibri could remain an impressive experiment. The larger idea is already spreading. Memory mapping has long allowed runtimes such as llama.cpp to access models larger than available RAM. Colibri pushes further by making expert placement and prefetching aware of the model's router. Anti-Res, the creator of Redis, has also built a focused C and metal inference engine called DS4. It supports SSD streaming for models that exceed available memory. Other inference projects are exploring expert caches and additional memory tiers. The direction is clear. AI inference is no longer only a question of how much GPU memory a machine has. It is becoming a placement problem. Which weights must remain close to the processor? Which ones can wait in system memory? Which ones can stay on disk until the router predicts they are needed? For the cost of a consumer SSD, a person can at least touch a model that once belonged exclusively inside expensive infrastructure. Touching is not the same as running it well. Colibri does not make a laptop equivalent to a GPU cluster. It breaks the requirement that the whole model must fit before anything can happen. That distinction is easy to laugh at when the output takes hours. It may look much less funny if prediction improves, SSD bandwidth rises, caches become smarter, and sparse models grow even larger. The future of local AI may not be one perfectly sized model sitting in RAM. It may be a huge model spread across GPU memory, RAM, and storage, with every parameter living on the cheapest tier that can deliver it in time. So choose your side. Would you rather rent instant access to a frontier model through the cloud, or own a much slower version that never sends your data anywhere? I would take the slow machine for more tasks than I expected.